So we're going to talk about the simple gas laws. Simple gas laws describe relationships between a pair of properties of gases. And so the four basic properties of gases are pressure, symbolized with a capital P, volume with a capital V, temperature with a capital T, and amount of gas in moles with a lowercase n. That maybe doesn't make a lot of sense. Think of n for number of moles. So these properties are interrelated. You change one, it changes the others. So in the simple gas laws, we're just looking at a pair, say pressure and volume. What happens to the pressure if I change the volume? And in order to look at that, we have to keep the other two properties the same or constant. So the first law is Boyles Law, and this relates volume and pressure. Now, I talk about Robert Boyle. He lived in the 1600s. I think it's good to have heard his name and have an idea that he lived a really, really long time ago. I mean, this was before our country was a country, right? It was a long time ago. I am not going to test you on these guys' names. I'm not going to ask you to state Boyle's Law. I personally have a hard time remembering which is Boyle's Law and which is Charles' Law and which is Gay-Lussac's Law. I know the laws and I know how to use them. And if I wanted to know who created them or figured them out, I could go look it up. But I do know the guys' names and know that they studied gases. So I'm not going to test you on chemical history here. So here we have an illustration of the sorts of experiments that Boyle did. So here you can take a J tube, and it's capped at one end, and there's a gas here, and there's some mercury in here, and we can tell from the difference in these levels that the gas inside this end of the tube is higher in pressure than the atmosphere because it's pushing down. If we add more mercury to this tube, we can increase the pressure on that gas, and we observe that the volume gets smaller. The volume here could be measured by knowing the inside diameter of the tube and measuring how tall the gas is. You could use the geometry to calculate the volume. So adding mercury here, this gas squishes together, but the difference in the heights increases. And so that tells us now that this pressure is larger than it was over here. So the pressure goes up, the gas gets smaller. This is an inverse relationship. When one thing gets larger, the other things get smaller. So we like to graph our data because it helps us to see it visually instead of trying to figure out patterns in numbers. So here we have the volume of the gas as a function of its pressure. So we see that the volume gets smaller as the pressure gets larger. But it's not a linear relationship. It's exponential. It's a curve, right? And so we can see that this is getting smaller and smaller. But to get to zero volume, you'd have to get up to a really, really, really high pressure. Actually, you can't get to zero volume. So we say that Boyle's Law says that the volume is proportional to 1 over the pressure. It's inversely proportional. The volume is proportional to the inverse, the upside down, the 1 over of the pressure. So when we graph volume versus pressure, we get a curve. But if we graph volume versus 1 over the pressure, we get a straight line. So I'll come back to this slide. But this is like Boyle's data, volume versus pressure. But if we graph volume versus 1 over pressure, now we get a straight line. And that's much easier to deal with, to model, because we can use linear regression and get an equation for that line. And then we can predict, well, if the pressure was here, what would its volume be, etc. So as the pressure increases, the volume decreases by the same factor. So we can say that pressure times volume is equal to a constant. If that's the case, then for the same sample of gas, if you take the pressure times the volume under one condition, that's going to be equal to the pressure times the volume under a second set of conditions. And so this is how we typically express Boyle's Law. P1V1 equals P2V2, which is really similar to the dilution equation, M1V1 equals M2V2, but There's not really a relationship between those. So let's think about what the particles are doing to see if we can understand the idea behind Boyle's Law. So here we have a container, and the lid is movable, and so we can change the volume of this container without letting any gas in or out. So here there's a 1 kilogram weight sitting on this lid to keep it down. And here we have a pressure gauge telling us that the pressure is 1 atmosphere. The volume of this container is 1 liter. If we increase the pressure, well, we put more mass on the lid and cause it to squish down, we can cause the volume to be cut in half. Volume is half as large here as it was over there. If this is cut in half, then the pressure doubles. So it changes by the same factor. One gets larger, one gets smaller. So now the pressure is 2 atmosphere. Why does the pressure go up? Well, the concentration of gas particles has increased. There are the same number of gas particles in a smaller volume, and so they're going to run into the containers more frequently. In fact, twice as much. Boyle's Law also has implications for scuba diving, and there's very good reason why they make you take classes and get certified before they let you scuba dive, because it's a lot more complicated than it seems at the beginning. And if things go badly when you're 30, 40 meters under the water, there's a good chance that you could kill yourself, right? So they don't want people doing that. So here we have a picture of a diver at the surface. Right up here at the surface, this would be the ocean, so this is sea level up here, right? So the pressure up here is 1 atmosphere. As you go under the water, there's still atmospheric pressure up here, but you also have pressure that the water is putting on you. And water is more dense than air. And so as you go down under the water, for every 10 meters that you descend, the pressure increases about 1 atmosphere. So at the surface, we have a pressure of 1 atmosphere. At 10 meters is 2 atmospheres. At 20 meters, the pressure is 3 atmospheres. Now, if you had a long tube to the surface, like I don't know if you guys remember the Flintstones, but there's an episode of the Flintstones where Fred and Barney are underwater and they're breathing through reeds out and they're hiding from somebody. Well, if you're not down very far, that could work. But if you're down here 20 meters under the surface, the external pressure being put on your lungs is 3 atmospheres. That's 3 times as much as at the surface. And so even if you have a tube to the surface so that you could breathe, you're not going to be able to breathe because you're not strong enough to expand your lungs against that pressure. So to dive down and be able to breathe and stay alive, you need pressurized air to breathe. So as you descend, you need to breathe pressurized air, and of course the pressure needs to change as you go down. So you can see how things can get pretty complicated. If you take a breath down there 20 meters below at 3 atmospheres of pressure, and you hold your breath and you ascend quickly to the surface, bad idea. Your internal organ damage, extreme pain, because the volume of air in your lungs is going to try to triple. Your lungs weren't designed to do that, to triple in volume. Yeah.
Well, like the air that you've been in your blood, something.
There's also issues with air in your blood, and especially with the nitrogen in your blood, and we'll talk about that later when we talk about gas mixtures. Yeah, it's called the bends. Essentially, the nitrogen boils out of your blood. Yeah, not good. So, if you're diving, you should always exhale as you're rising. I'm not going to test you on that, but I think it's interesting. Okay, so here's our first simple gas law problem, and it's not a simple problem. It's a complicated problem. Well, that's okay. This is Chem 1A, right? We can do this. So we're going to read all the words, and then for this problem, we're going to draw a picture because Sometimes we just need a picture, even if it's a really, really ugly picture. Your mind can straighten it out a little bit, and then you can just kind of see what's going on. So a snorkeler takes a syringe filled with 16 milliliters of air from the surface, where the pressure is 1 atmosphere, to an unknown depth. The volume of the air in the syringe at this depth is 7.5 milliliters. What's the pressure at this depth? If the pressure increases by 1 atmosphere for every additional 10 meters of depth, how deep is the snorkeler? So let's draw a picture. So we're diving, we're snorkeling. So there's the surface of the water. And up here, the pressure is 1 atmosphere. And there's a syringe. Now, the needle would not be on this, it would be capped off. So there's a syringe with some air in it, and we're told that this has a volume of 16 milliliters. I'm not even going to try to draw the snorkeler. I'm just going to stick with the syringe, because that's ugly enough. So as he takes the syringe down lower and lower, the pressure increases on the outside of the syringe, and that causes the plunger to get pushed in, much as the same way as if you were just holding the syringe and putting pressure on the plunger. The end of the syringe is closed, and you can squish the air, right? You could squeeze it a little bit. So here, the atmosphere plus the water is putting pressure, and down here at this unknown depth, the volume has gotten smaller. It's 7.5 milliliters. So this is a volume, and this is a volume. This is a pressure, and they're asking us, what's the pressure at this depth? What's the pressure down here? So this is one set of conditions, the pressure and the volume here together. Here is another set of conditions, a different pressure and a different volume. I'm going to call the top one 1 because it happened first, and I'm going to call the bottom one 2 because it happened second. It doesn't really matter, but... So then I need an equation that has P's and V's with 1's and 2's. And that's the equation we just learned about, the only one we know so far. P1 V1 equals P2 V2. R2 D2 and C3PO. We're trying to find P2. So that's this guy right here. So we're going to need some algebra in this chapter. We need to be able to rearrange simple equations, just multiplying and dividing. Some of you are great at this, some of you suck. Okay? It's not your fault, it's just how your brain works and how they screwed you over in elementary school. So if you're not good at this, you know who you are, please come and ask me for help. Just very startled by this. Please come and ask me for help, because you can get good at this. It might never be fun or easy, but you can get good at this. And I will explain it to you using different crazy analogies until you say, oh, I see it now. And then you'll feel so good. But you have to come and ask, okay? So I'll give my standard explanation here. So I want P2 by itself. And yes, you can put the numbers in and then rearrange it. I don't recommend that. Bad things happen when people do that. Let's rearrange it with the letters, because it's just so much simpler. So I want to get P2 by itself. I need to get rid of the V2, and so I'm going to divide this side by V2. Because V2 over V2 is 1, it cancels out. But this is an equality. Both sides are equal, and so if I do something to one side, I have to do the same thing to the other side. So if I divide one side by V2, I have to divide the other side by V2 for them to still be equal. And there I have it. It's messy, and the P2 is on the wrong side, so I'm going to rewrite this. So P2 is equal to P1 times V1 divided by V2. This is part of showing your work. You should always show the rearranged equation written out, and then you take your numbers and you plug it in. So our numbers, well, we've identified what those are over here. Here's pressure 1 and volume 1, so we're going to put those in here. We always include the units. So 1 atmosphere, and the volume is, actually that's 1.0. I was kind of sloppy with that. That's 1.0. Here, this is 1.0, because that's what it says right here. 1.0 atmospheres. And the volume is 16 milliliters. And down here with the unknown pressure, the volume is 7.5 milliliters. And then we look to see what happens with the units. Well, the milliliters cancel each other out. So when I do the math here, I'm going to end up with a unit of atmospheres. So I've got 1 times 16 divided by 7.5. 2.133 repeating. That would have 2 sig figs. So stop there, atmospheres. So the first question, what is the pressure at this depth? Pressure is equal to 2.1 atmospheres. That's the first answer. Yeah. That's the more straightforward part of this problem. The second part requires a little more thinking. So the pressure increases by 1 atmosphere for every 10 meters of depth. How deep is the snorkeler? Well, you can kind of estimate that, just kind of thinking about it. It's like, well, we started at 1 atmosphere up here, and then when we go down 10 meters, we add an atmosphere. So when we go down 10 meters, we get 2 atmospheres. But this is 2.1, it's a little further. So if we were just ballparking, we could say, well, it's about 10 meters deep. But we can do better than that. This is actually a disguised conversion factor. 1 atmosphere for every additional 10 meters. So 1 atmosphere increase is equal to 10 meters of depth. Well, how much has the pressure increased? Has it increased 2.1 atmospheres? No, the pressure is 2.1 atmospheres. What did it start out as? 1 atmosphere. So the increase in pressure is the pressure down here minus the pressure at the surface. So the increase in pressure is 1.13 atmospheres. Okay? That's how much the pressure increased. So I can take that 1.13 atmospheres and apply that conversion factor, that 10 meters for every 1 atmosphere. Oh my goodness. So about 11 meters. Any questions? So the first part of this is fairly straightforward, although you got to think about this weird thing happening. The second part's a little bit tricky. You absolutely need to be able to do the first part of this question to pass the class. .1 atmospheres, 11 meters. Okay, second simple law, Charles' law. Charles studied relationship of volume and temperature. This guy lived in the 17 and 1800s. Again, this stuff happened a long time ago. So he looked at the relationship between volume and temperature of a gas, and he found that the volume of a gas is directly proportional to its absolute temperature. So different ways of expressing Charles' law. The volume divided by the temperature is a constant. or we typically use it this way, V1 over T1 equals V2 over T2. Very important thing here, though, is the temperature must always be expressed in kelvins. Always. Volume doesn't really matter what unit you use. You need the volume units to agree. But in gas laws, temperatures always have to be in kelvins. They will frequently give you the temperatures in Celsius. They'll sometimes ask you for the temperature in Celsius, and you have to just convert it back and forth. So here's an example of some Charles Law data, and this helps us to understand where the Kelvin scale came from. So here, measuring the volume of a gas as you change the temperature. So here is if we have 0.25 moles at 1 atmosphere of pressure, because those things have to stay the same. We're going to change the volume and the temperature, the amount of gas and the pressure has to stay the same. So we can see this straight line for 1/4 of a mole, and if we have 1/2 mole of gas, we get a line like this, and 1 mole of gas, and we get a line like this. So these dots are the actual data points where things were measured. Here, temperature is listed in Celsius and in Kelvin. So this was done Celsius starting at the freezing point of water and increasing from there. This is where the data ended. The problem with gases is you get too cold and they condense into liquids, and then it doesn't work anymore. So you can't actually have data down here because the gas condenses into a liquid. But we can extrapolate. Extrapolation is taking your data, predicting where it would go past where your data is. So that's the dashed lines here. So we extrapolate, and what we find is that these 3 lines intersect at the same temperature. They would hit 0 volume at minus 273.15 degrees Celsius. So it looks like that's the lowest possible temperature there could be. And you can do this with other other pressures, other amounts of gas, and they're all going to intercept at minus 273.15 degrees Celsius. So that's what we call absolute zero, and that's the basis of the Kelvin scale. So they said, well, let's just make that 0 and go up from there.
So that's when there's absolutely no movement.
Yes, so absolute 0 is a temperature which all motion stops. So the particles are not moving at all, not even vibrating. So if it was students, they wouldn't be breathing, your heart wouldn't be pumping, nothing, literally frozen, right? Completely frozen. Now, if you took this gas sample and made it colder and colder and colder, could you make 1 mole of gas have 0 volume? No. You could have it be a very small amount of volume, but the gas gets smaller and smaller. You're squeezing the extra space out of it, but eventually you're going to get a liquid, then a solid, and those particles actually have volume. And so you can't take a gas to 0 volume. But it looks like you can from the data. And we'll look at what happens down here with real gases later in the chapter. But that's where the Kelvin temperature scale came from. So put 0 here, and then the size of the increment is the same. A Kelvin and a degree Celsius are the same size. Another important thing about this Kelvin scale is we're never going to have negative temperatures. If you throw a negative temperature into V1 over T1 equals V2 over T2, you'd end up with some negative volumes. And that's even more ridiculous than 0 volume. You could have 0 volume if you don't have anything in there, not even 1 molecule, but you can't have a negative volume. It's not possible. Yeah?
Why do we teach all the laws separately and not just the ideal gas law? Since all the laws are in the ideal gas
Well, that's a good question. So why do we teach these laws separately when they're really all in the ideal gas law? I think it's because it's easier for us to look at just 2 things changing. We change this, and this one other thing changes, and we see these relationships. The interrelationship of 4 variables is a bit complicated. But I will show you how all these laws come together and how we don't actually need to memorize the individual laws because they can be derived very, very easily from the ideal gas law. So if we look at a molecular view of Charles' law, and this is something you could try at home, take a balloon, kind of medium-sized balloon, stick it in ice water. It'll shrink, it'll shrivel, it'll get smaller. Because what's happening here is when we make the gas cold, we reduce the kinetic energy of those particles. So this is those kindergartners, and it's nap time. You know, they had lunch and they went out to recess and they're tired, right? They are low energy. They are not running. They're kind of walking around the classroom and they're just not going to bump into things as much, right? So this balloon is going to have a constant pressure. So in order for the pressure to be the same, with the particles moving more slowly, it has to get smaller. Here, boiling water, this is like giving those kindergartners a Red Bull. Not a good idea. High energy now, they're zinging around, and if we want to keep the number of collisions the same, we have to let them occupy a larger room. So we increase the energy of the gas particles, and the volume will expand if the pressure is the same. Does that make any sense? A lot of these gas law things we can understand if we just think about balloons. You know, what happens when you heat up a balloon? Well, it gets bigger. What happens when a balloon gets colder? It gets smaller. Yeah, I kind of said that. So here's that same balloon in some liquid nitrogen, and it's just going to like shrivel up and get really, really small. And then this is a hot air balloon. I remember being puzzled by these as a child because I knew, you know, in the cartoons, you see cartoon characters and they'll blow up a balloon and it'll float. They didn't use a helium tank, they just blew into it and it floats. Yep. Cartoonists love to violate the laws of physics. I mean, it's just like a game to them, I think. So I knew that didn't work because you blow up a balloon and it just falls to the ground. It has to have helium in it to float, right? And also, if the balloon has holes in it, the air won't stay in and it'll shrivel up and just be useless. So then, explain this one. Here we have a balloon with a ginormous hole in the middle of it, and it's not full of helium, it's full of air, and yet it's floating, and it picks up this basket and a bunch of people too, right? As a child, you're like, what the heck? It's like magic, right? How does that even work? Charles' Law. So here in the hot air balloon, it's a hot air balloon, and the hot is the key. So big, ginormous burner here to heat up the air. You heat up the air, the particles move faster, and the pressure would increase, but because there's this giant hole, the pressure cannot increase. Some of the gas escapes. Essentially what happens is the gas is expanding, it's getting larger. There's more space between it, that changes its density. And so the gas inside of this hot air balloon, when it's hot, has a lower density than the air outside. And so this is like a bubble in water rising because the bubble of gas has a lower density. Here, this balloon full of hot air has lower density, and so it floats in the air around. And you can control it going up and down by changing the temperature of the gas. Now, you have no control over direction. You're at the mercy of the winds. And so there are winds that happen at different levels, at different speeds, and so you can kind of control it by going up and down, but yeah, it's kind of a crapshoot there. Yes?
Is that like the explanation of why you say that hot air rises and cold air falls?
Yes. Hot air rises and cold air falls. And people have taken advantage of that over the years, I think with not really thinking about the chemistry of it, but in the South, the old plantations, the rooms had very tall ceilings. And it's really hot and humid and miserable there in the summer, and they didn't have air conditioning back in the olden days, right? So if you have a high ceiling, it lets the hotter air rise to the top. And then they also had a lot of things where they had the door and there was a window above the door. And you could open that window and that would let the hot air at the top of the ceiling move out and allow some slightly cooler air from outside to come in. It's also why the ceiling fans can go both ways, so that you could pull air up from the bottom or blow air down from the top.
So as part of the reason, so we know this is a combustion reaction, is there, there's obviously water that's formed and then there's carbon that's broken apart, right? So is part of the reason why it rises also because carbon is less dense than oxygen?
No.
No?
No. There is combustion here happening, but the gas products from that combustion, I think compared to the volume of air in the balloon, are not having much of an impact at all. The big deal is that the temperature is changing. Carbon monoxide. We'll talk about gas densities later. I could go on and on and on and on, and then we end up not having enough time for lab. So, any other questions? So let's do a Charles Law problem. This one's a little more straightforward. Be a lot of problems with cylinders with movable pistons because it's a convenient container that's the size can change. So gas in a cylinder with a movable piston has an initial volume of 88.2 milliliters. If we heat the gas from 35 degrees Celsius to 155 degrees Celsius, what is its final volume in milliliters? So this one I don't think we really need to draw a picture of. It's a little more straightforward. But we do need to collect the numbers and make some sense out of them. And so I think it's useful to make a table. So I'm going to make a table. And we're going to have 2 rows in our table. And I'm going to call the first row 1 and the second row 2. I'm not trying to be confusing. So I'm going to read through the problem again and just collect the numbers. The first number I come to is 88.2 milliliters. So I'm going to write this up here, 88.2 milliliters. Very important to put the unit in there. And that's going to be a column. And I ask myself, well, what quantity is that? Well, that's the volume, right? It actually says volume. So I'm going to label this column V for volume. If it didn't say volume, if it just had the unit milliliter, I should recognize that milliliter is a unit of volume, so I could identify it that way. And then I've got 2 temperatures. I've got 35 and 155. And what's important is I need to pick the one that goes with the 88 to put it on the same row. So this is the initial volume, and we're heating the gas from 35 to 155. So the 88.2 milliliters happens at the 35 degrees Celsius, and the 155 is the other condition. And these are temperatures. And it says, what's the final volume? And so in this table, there should always be one box that's blank. And so I'm going to call this V2 because it's column V and it's row 2. Before we do anything else, though, what unit do we have to use for the temperature? Kelvin. So before we start calculating and forget to do that, as soon as we write down Celsius, we got to change that to Kelvin. Now the book gets a little sloppy with the sig figs, and I've decided I'm just going to try to be consistent with the book. So the conversion is 273.15, right? But here, the temperatures, there's uncertainty in the ones place. And this happens a lot, and so then it's easier to just use 273 because the 0.15 is small. I don't like it, but that's what they do. So 35 plus 273. You are very welcome to use 273.15. You should still get the same answer. So here, this is going to be 308 Kelvin. And I also need to convert my other temperature. So 155 plus 273 is 428 Kelvin. So there I've got my nice organized table, and this, of course, is a Charles Law problem because it says so up there. On the exam, there'll be Charles Law and Boyles Law, and it's not going to have them labeled for you. So you have to know which equation to pick. Well, I need an equation with V and T and 1 and 2. And of course, that's the one we just learned about. V1 over T1 equals V2 over T2. This equation is dangerous because it has fractions in it. And people don't do well with fractions. They say that 4 out of 3 people have trouble with fractions. Yeah. Yeah. Slow burn there. So if you're good with fractions, you can take this equation and solve it for V2 and just write it down. And if you're curious how you can do that, I'll be happy to show you. But for the rest of you, let's cross multiply to get rid of the fractions and then rearrange the equation. So in case you forgot, cross multiplying is you take the top of one side of the equation and you multiply by the bottom of the other side. So V1 times T2, and then the bottom of the first side times the top of the second side. You see how that makes a cross? So we've got T1 and V2. And those are equal. I cross multiplied. It looks different, but it's the same thing. Now I can rearrange without worrying about screwing up fractions. I'm trying to solve for V2. That's this one right here. And so I want to move things from that side of the equation. I want to move T1 over here. So I'm going to do that by dividing by T1. T1 divided by T1 is 1. Cancels out. And I have to do the same thing to the other side. And there I've got my equation. So V2 is equal to V1 times T2 divided by T1. Now, I think you can see how it would be really, really easy to mess up the 1s and the 2s. So it's important to write stuff down and go back and double check, because if you switch the 2s and the 1s, then you're going to get the wrong answer. So there's my equation, and then I'm going to fill it in. So volume 1, I'm going to go look and find volume 1 on the table, 88.2 milliliters. And then I want T2, which is 428 Kelvin. And in the bottom, I've got T1, which is 308 Kelvin. And I look at the units to see what happens. Well, the kelvins cancel out. I actually screwed this one up yesterday, so let's see if I can do it correctly today. 88.2 times 428 divided by 308. So 122.56 milliliters. Everything's got 3 sig figs, which is pretty common. And so we're going to say that the answer is 123 milliliters. And we can ask ourselves, well, does that make sense? I had a gas that was 88 milliliters, and I heated it up. Do I expect it to get bigger or smaller? Bigger. And it did get bigger. So that's encouraging. If you got your 1s and 2s backwards, what usually happens is the change goes in the other direction, and then that's sort of a warning that, hey, I need to check something out here. Yes?
Say they gave us V2 instead of V1, if we go like that, this one smaller, like
Yes, if we were given this and we're calculating V1, we should get a smaller number. So, quick lesson in rearranging here. We can take this relationship and make this without writing stuff down by recognizing that you can move something from the bottom of one side through this X to the top of the other side. So I can take this T2 and just move it up over here. And then I've got V2 equals T2 times V1 over T1. And so that's how people can rearrange these things in their heads. But if you can't do that, don't worry about it. Just learn how to do it by writing it down. Any questions? 123. So a lot of us have gotten good at learning how to use equations and do a calculation, and so we can do that. You give me real numbers and I'm fine, and then I give you a question like this on an exam and you're like, there's no numbers. The pressure exerted on a sample of a fixed amount of gas is doubled at constant pressure, and then the temperature of the gas in kelvins is doubled at constant pressure. What's the final volume of the gas? It's the same. How do we know that? Well, we can just think about what happened. So I've got a fixed amount of gas, and I double the pressure. So if I go times 2 pressure, what does that do to the volume? Wait. I increase the pressure times 2. Then the volume goes down by a factor of 2, right? So the volume is now 1/2 what it was. And then it says I double the temperature. So if the temperature goes up times 2, what does that do to the volume? Makes it go up. So I had this 1.5, and now I'm going times 2 to that, and so I end up with back to 1, what I started with. So the answer is that the final volume is the same as the initial volume. Some people have a lot of trouble thinking about stuff like that. So what you can do is you can make up numbers that match the description. So the pressure is doubled. Well, I can say, well, my initial pressure is 1 atmosphere. And so my volume is this, and then I'm going to, my volume is 1 liter. And if I double the pressure, so my pressure is 2 atmospheres, then I could actually calculate the volume. And then you can put some numbers in for the temperature and do the same thing. But a question like this helps us to identify, do we really understand what's going on? Any questions? So the last simple gas law we're going to talk about, Avogadros Law. And this is the same guy of Avogadro's number. He lived in the 17 and 1800s. And he was the first one who stated the relationship between volume and amount of gas in moles. And Avogadro's number is named for Amadeo Avogadro, even though he did not actually determine what the number was. That came later. But his observation was that the volume of a gas is proportional to the number of gas molecules. Now, I think we all recognize that if you take a balloon and you put more air into it, the volume expands, right? And so you increase the amount of gas and the volume increases. What was groundbreaking about this is that it's the number of gas particles, gas molecules. It's the number of pieces. It actually doesn't matter what size the particles are or what they weigh. The volume is the same no matter what the gas is. And that's weird. It's very strange. So Avogadro's law is often given this way. Looks a lot like Charles' law. V1 over N1 equals V2 over N2. So here we're counting the number of gas molecules using moles. So N is the number of gas molecules in moles. Equal volumes of gases contain equal numbers of molecules. It doesn't matter what the gas is. That's not true of liquids and solids. So here we have a graph. The volume of a gas is proportional to the number of moles. So if we double, say from here, from 0.4 to 0.8, if we double the number of moles, then we double the volume. If we take this information and extrapolate to 0, it predicts that 0 moles of gas would occupy 0 volume. Well, that seems reasonable. A container with nothing in it could have zero volume. Another conceptual question. Which action causes the volume of a gas sample to increase? If we decrease the pressure of a gas, what does that do? It lets it expand out, right? Okay, so there, that one answers it. Sometimes there's more than one correct answer. Decreasing the temperature. If I take that gas sample and I make it colder, what does that do to the volume? Makes it get smaller. So not that one. Decreasing the number of moles of gas. So I take that balloon and I take some gas out of it. It gets smaller. Duh. So then none of the above can't be the right answer either. Any questions? So here's an Avogadros Law problem. Chemical reaction occurring in a cylinder equipped with a movable piston, there's that thing again, produces 0.621 moles of a gaseous product if the cylinder contained 0.120 moles of gas before the reaction and had an initial volume of 2.18 liters. What was its volume after the reaction? Assume constant pressure and temperature and that the initial amount of gas completely reacts. That's the fine print. Okay, I read the problem. It's like, numbers. Let's pull numbers out and organize them in a table. So, the first number I come to is 0.621 moles. 0.621 moles. And so I need to label this column. What letter represents moles of gas? N. So this is lowercase n. That's really a crappy n. There we go, n. If the cylinder contained 0.12 moles before the reaction, okay, there's another mole. I'm going to put that in here, 0.120 moles. And had an initial volume of 2.18 liters. So we have to look at these numbers. So here I've got 0.12 moles before the reaction and initial volume of 2.18 liters. These two go together. Do you see that? So that volume of 2.18 liters goes down here. I'm going to label this volume. And so what I'm trying to find is up here. What was its volume after the reaction? Now, I can call this V1, and I can just use it as labeled and solve it, and that's what I did yesterday. And some people are like, oh, I find that confusing because it's the second thing, and you called it 1. Well, so if you don't like that, let's just relabel our table. Let's call this 2 and that 1. The numbers are just so that we can pair these two things together. And so if you want to change them, if you wanted to call them 3 and 5, you could do that, which is why, but you could. So I'm just going to label this differently because it's more intuitive that way. So we're solving for V2. So I have n's and v's. I need an equation that has n's and v's. So V1 over N1 equals V2 over N2. So we can cross multiply and rearrange the equation, or we can think about moving stuff, and I want V2 by itself. It's this guy up here. And so I'm going to take this guy and I'm going to move him diagonally to the other side of the equation. V2 is equal to V1 times N2 over N1. And now I'm going to take my numbers and plug them in. 2.18 liters, N2, 0.621 moles, and N1 is 0.120 moles. And I'm checking out my units, and the moles cancel out. Sometimes the problem will give you different, like liters and milliliters, and then you have to do some unit conversions. So 2.18 times 0.621 divided by 0.12. .2815 liters. Looks like 3 sig figs. 11.3 liters. And with these simple gas laws, we can always ask ourselves, well, does this make sense? I had an initial volume of 2 liters, and I had 0.12 moles. And in this chemical reaction, I increased the moles of gas. So I have more gas. Pressure's the same, temperature's the same. I expect that the volume of the gas would get larger, and it did. So that's encouraging. Any questions? .3. Okay, and then this is a fun one. This is one that we're going to have to draw pictures for. Scale model of a blimp rises when it's filled with helium to a volume of 55.0 cubic decimeters. When 1.1 mole of helium is added to the blimp, the volume is 26.2 cubic decimeters. How many more grams of helium must be added to make it rise? Assume constant T and P. Well, let's draw a blimp. So this blimp is going to float. I know my blimp kind of looks like a fish. It's okay. It's going to float when it's got enough helium in it. 55 cubic decimeters. So it started out all flat. This reminds me, I actually bought one of these for my kids one year for Christmas. It was actually pretty fun. Yeah, so it's like this Mylar balloon, basically, but then you have to put helium in it. And if you just put a little helium in it, it kind of starts to puff up, but it won't float. You have to get enough helium in it for it to rise. So down here, what we have is we have 1.1 moles of helium in there, and its volume is 26.2 cubic decimeters. It's not floating yet. We want to know how many more grams of helium do we have to add to make it rise. Now, doesn't that seem a little weird? I'm going to add mass to this thing and it's going to float? Yeah, it will. Well, let's just label what we've got here. This is N, number of moles, right? And this is a volume. And up here I have a volume. And so, without thinking about exactly what the question is, what could I solve for? What could I calculate up here? The moles, right? So if I call this N1 and V1, and this is V2, I could calculate what N2 is, right? Could use Avogadros Law. V1 over N1 equals V2 over N2. This involves a little more moving about. I'm going to take this one up there and this one down here and move this one up there. That's real clear, right? N2 is equal to N1 V2 over V1. You might want to cross multiply and straighten that one out. Well, N1 is 1.10 moles. V2 55.0 cubic decimeters. That's an entirely valid volume unit. We're just not used to it. Don't see it very often. 26.2 cubic decimeters down here. Look, the cubic decimeters cancel out, and so we're not going to have to worry about those anymore. So what I end up with here is a 2.3091 moles. I need to add helium until I get 2.3091 moles of helium, and then this blimp's going to float. Everybody okay with that? Have we answered the question? No, not yet. We're getting closer though. So the question is, how much gas needs to be added? And not how many moles, it wants to know how many grams. So I had 1.1 moles and I need 2.3091 moles. So how many moles do I need to add? Well, the difference, right? Let's use green. So I need 2.3091. I'm not rounding yet. That's what I need to have, and I started out with 1.10 moles. So that tells me I need to add 1.2091 moles of gas, right? That's how much I need to add. And then how can I figure out the mass of that? It's helium, right? Periodic table. Yeah, I'll do it over here. So 1.2091 moles of helium, and I can convert to grams using the molar mass of helium, which is conveniently located on the periodic table. And I get 4.84026 grams, 4.84 grams of helium need to be added. Any questions? I pretty much guarantee there will be a question like this on the exam where it's talking about adding gas, and it seems like a trick, and maybe it is a trick, but I'm telling you I'm going to try to trick you with this. So then you're going to learn how to do it, and then you won't be tricked, right? How much are we adding? So we use the gas laws to calculate, well, what's the final, what's the initial, and then to find out how much is added, we have to do some subtracting.